So hello everyone, and I would like to thank the SFTech committee for choosing our article to be a candidate for the Piotr Prize. I'm going to talk about the Earth-Air heat exchanger in the context of energetic and exergetic analysis, and this work was done by me, my supervisor, Professor Monica Sirou, and co-supervisor, Dr. Jian Lim. So what are the Earth-Air heat exchangers? They are a kind of shallow geothermal systems. It's a simple heat exchanger buried under the ground. It uses air as a heat transfer fluid, and the air enters from one side, as we can see in the pictures. It gets heated or cooled by the surrounding soil, and then it is either used directly inside the building or it is more processed using auxiliary systems. The Earth exchanger is a passive system that uses low amount of, that decreases the amount of energy used and can thus decrease the CO2 emissions. So there are different types of Earth-Air exchanger, and they can be classified according to pipe layout and design. They can be vertical, horizontal, or it could take other shapes as shown in the picture. And they can be also classified according to circulation mode. It could be an open loop or closed loop mode. And finally, can be classified according to operation mode, where it can work for heating, for cooling, or for both, depending on the season. So our work is dependent on an experimental Earth-Air heat exchanger, which is found at Campus del Kirch and University of Strasbourg. It is a horizontal Earth-Air heat exchanger. It is, its depth varies between 0.7 to 1.2 meters, and it's 29 meters long. It works in open loop mode, and it works for heating and cooling depending on the season. So our Earth-Air heat exchanger is divided into three sections. Each section is coated by a different type of soils. The first section is coated by sand. The second section is coated by a sand and bentonite mixture that helps to preserve water and moisture inside the soil. And the last section is coated by a natural soil-like fill that's found near the site. In each section, we have at the middle of the section a set of temperature sensors and humidity or moisture content sensors. You can see in the picture the cross symbol represents the position of the temperature sensors, and the star symbol represents the position of the humidity sensor. We also have a measurement of the humidity and relative humidity, of the temperature and relative humidity at the inlet and at the outlet of the system. All these measurements are monitored and recorded using a LabVIEW program. It permits us to remotely monitor the system, and data were recorded every 20 minutes from 2012 to 2019. Now I'm going to talk about the analysis methodology that we followed to make the energy and exergy analysis of the system. So the system is very simple. We have a pipe. We have at the inlet a filter to filter any dust in the air. And at the outlet, we have a fan to blow the air inside the pipe. So in order to find the heat transfer rate between the air passing in the system and the soil around it, we applied an energy balance to the control volume of the pipe only, which can help us to find the heat transfer, which is Q in the equation, and just using the inlet and outlet enthalpies of the mass flow rate. And these enthalpies were determined according to the temperature and to the moisture content of the air. Now talking about exergy, what is exergy in general? So by combining the first and second law of thermodynamics, we can have the exergy balance, or results in exergy balance. So exergy is the maximum amount of work that can be produced by a stream or a system as it is brought to equilibrium with the reference environment. In other words, exergy is a measure of the available energy. And we can imagine it as that like the whole circle is the total energy, and part of this circle is the exergy, and the rest will be the unavailable energy. So the available energy is limited by the second law of thermodynamics, and also this available energy can decrease when there are irreversibilities in the system that can generate entropy. And this decrease in available energy is usually referred to as exergy destruction. So now again, applying the exergy balance to the whole system results in the following equation that takes into account the exergy of the heat, the work of the fan, and the mass flow rate at the inlet and the outlet, and the exergy destroyed in the system. So substituting each term of exergy results in the following equation. You can see in this equation that exergy affects the heat transfer and the mass flow rates, but the work remains the same. And the work of the fan is just the electrical work of the fan multiplied by its efficiency. And I will also show you the equation for calculating the flow exergy, which is the exergy of the mass. This equation takes into account the temperature, the pressure, and the humidity of the air at the inlet or at the outlet. So as we have seen that calculating or applying the exergy balance to the system permits us to find the exergy destroyed in the system. So now we applied this exergy balance to the different components of the system so that we can find the exergy destroyed in each component separately. So applying it to the filter, for example, can give us the exergy destroyed in the filter, and as so we do for the pipe only and for the fan, and we can then find the three destroyed exergies in each component. Finally, we were able to find the coefficient of performance, which is a kind of energetic efficiency that takes into account the energy that is taken from the system divided by the energy consumed in this system. And also we have the exergetic efficiency, which to be able to understand exergetic efficiency, we can say that energy systems usually are not 100% efficient, even in the perfect reversible conditions, and this is due to second law of thermodynamics. So the exergetic efficiency is an efficiency calculated in reference to the maximum capability of the system, which is the reversible in the reversible conditions. So we can say that exergetic efficiency gives a more realistic assessment of the system. Finally, in the methodology, I'm going to talk about the reference state, because if you have noticed in the equations of exergy, we have to choose a reference state where the system equilibrates with. So this reference state is usually the environment around the system, and it is the environment that the system interacts with without this environment losing its intensive properties. In the case of air heat exchanger, it is sufficient to talk about a restricted dead state or restricted reference state, where we don't take into account the chemical interactions with the environment. And this is valid in our case because we don't really have chemical interactions between the system and the soil or the air around it. So we choose in our case the surrounding ambient air to be the environment or the reference state of the system, and because the temperature and the humidity varies a lot in the ambient air, we choose average values along the month where the analysis is being carried. So we have average values of temperature and the humidity along this month. And for the pressure, the reference pressure was taken as the standard sea level atmospheric pressure. We also need the velocity and the pressure, so we just measured them using fan anemometer for the velocity, and for the pressure using the pitot tube that can help us to find differential pressure at different points in the tube, and then using the ambient atmospheric pressure from meteorological data, we could find the absolute static pressure at each point. Finally, talking about the results, we have a set of results here. I'm first going to show the temperature variations. So this graph shows us the temperature at the inlet and at the outlet, and also the average wall temperature of the pipe. And you can see that this variation is during the first week of August in 2018. So it is a typical cooling period where we are cooling the air. As we can see in the graph, the variation of the temperature between inlet and the outlet. The inlet temperature is the blue curve, and the outlet temperature is the orange curve. You can see the variation that can reach up to 11 degrees Celsius on some days. In this graph, we are showing the heat transfer rate. As you can see, the values are in negative because it's cooling, and we are considering that the heat transfer is out of the system. You can also see that we have some zero values of this heat transfer. This is because of bypass, because the system was not functioning during the hours where the ambient temperature or ambient air temperature is lower than the soil temperature, and this mainly happens during the night, so the system is not functioning during these hours. We can see in this graph that the maximum heat transfer rate can reach up to 1,188 watt, and during the whole week we can retrieve about 65 kilowatt hours of energy using this system. So talking about exergy, in this graph we show the exergy destruction in each component of the system. You can see the red curve shows the exergy destroyed in the whole system, and the curves below it is for each component alone, the fan, the filter, and the pipe. We can see that the variation of the destruction in the pipe is high because it's mainly dependent on heat transfer, which is dependent on temperature that varies a lot. However, the highest exergy was destroyed in the fan, and it's mostly constant because it just takes into account the pressure difference that the fan makes. And finally, the performance assessment is done using calculating the coefficient of performance and exergetic efficiency. The graph shows us the orange curve, which is for the coefficient of performance. Its values are on the right, and we can see that the values varies a lot because it is dependent on the heat transfer again, so dependent on the temperature. And the variation could reach up to 36. However, looking on the exergetic efficiency, we can see that it is mostly constant. That's because the terms constituting the equation of exergetic efficiency compensate to one another when there is a variation in the system, and it's almost at an average value of 61%. As a conclusion, we can draw some main results where we have seen that about 65 kilowatt hour of heat was removed from the air to cool it using only 4.4 kilowatt hour of electricity. So the system can decrease the cooling expenses using free geothermal energy. And it was found that the exergy is mostly destroyed at the level of the fan, as we have seen, and that the system is really dependent on the weather and on the location where it is being used. So we can recommend that the fan should be mainly improved to lower the exergy destruction on the whole system and to improve its performance. And finally, the system profitability should be carefully studied in different locations and weather conditions, as this really affects the performance of the system. So here I just show some of the references that we used and some of our publications. You can also check our latest publication about the system just by scanning this code if you want. And thank you for listening, and if you have any questions, just do not hesitate to ask. Thank you.
Thank you.
You're welcome.
Thank you for this talk. Any question? In English, please. Any question? Yes.
Albert Hauck from heat exchanger company Hauck. Why did you use air and not water?
So mainly there are different types of the geothermal systems, and our system is using air because like in France, we use ventilation, or it's obliged to have an air ventilation inside the system. So we can pass the air inside the system before passing it in the air handling unit, so that we can decrease the energy cost for heating or for cooling. So it's mainly air-based system for air uses, for air ventilation mainly. But there are other systems using water. It could be for other things. So it's a different type. The depth, it varies between 0.7 meter to 1.2 meters. And the variation is to collect any water that can condensate on the pipe. So that's why we have the variation. Welcome.
Other questions?
You mentioned the existence of different proteins.
Yeah.
Could you say a word of the influence of the coatings because you have different sections?
Yeah, I should have mentioned that in this study we don't mainly focus on the effect of the different coatings, but in the other articles, like the second one and the third one, there were some results published about the difference or the comparison between these coatings. But we are using the same system. That's why I mentioned that the system has 3 different coatings. But it doesn't mainly affect here, or we didn't take into consideration the effect of each one. Yes, there's a question here.
Yes. Yes, is the system subjected to water condensation for solar utilization? If yes, what are the techniques used to remove that water?
Yeah, as I mentioned, there's a difference in the depth in the system, so it's not straight, it's not one level. It varies from 0.7 meter to 1.2 meters deep. So if there's any condensate, it will gather at the lowest point, and then we can use a pump to pump out this water. So yeah.
More questions? We have time for one question. Well, I have one. What are the uncertainties on the results?
Yeah, this is that we didn't consider the uncertainty.
Yeah. 65 kilowatt.
Yeah. We didn't have the uncertainty analysis of the results. We have all the uncertainties of the measurements, but we didn't yet make the uncertainty analysis on the final results. So it should be considered future.
Okay.
Yeah.